Alright, welcome back. This is Chapter 4, Part 3, okay, the last of this chapter in this module. And so we've been talking about a series of common chemical reactions, precipitation reactions, which form insoluble ionic compounds. We talked about neutralization reactions, which are water molecules that are formed from basically hydrogen ions and hydroxide ions being combined. And now we can take a look at what's termed oxidation reduction reactions, also known as redox reaction. All right, and specifically we concentrate on these redox reactions where one reactant is a metal in its elemental form, okay, so like manganese or magnesium. A reaction that transfers electrons from one reactant to another is called an oxidation reduction reaction. All right, and we can remember the definition of both oxidation and reduction if you just remember oil and rig. So oil rig, right? Oxidation is the loss, reduction is the gain. It's the easiest way to remember that. A few examples of oxidation reduction reactions include the green coating that forms from the copper oxidations, or we can look at the production of rust when iron corrodes, okay? Or when basically silver tarnishes. Well, one of the first things we need to understand is oxidation numbers, okay? So to determine if we have an oxidation reduction reaction and to help identify the substance being oxidized or reduced, we basically use a bookkeeping system for electrons, and these are called oxidation numbers. So there's really a set of rules for assigning the oxidation numbers, and I encourage you to spend some time to go through these. You don't necessarily need to memorize them, I will give them to you, but you should be able to apply these to individual substances or to a reaction and understand what's being oxidized and what's being reduced. Okay, I'd suggest you spending some time practicing this concept as well. Well, a specific type of oxidation reduction reaction that we can talk about and that we're going to see frequently are called displacement reactions because the ion in solution is displaced or replaced through oxidation of an element. So, for example, in the reaction of A plus Bx, basically see that A replaces B, okay, in the product through oxidation, okay. So displacement reaction will occur when a metal either reacts with either an acid or a metal salt. So here you have your metal in its elemental form, okay, it reacts with either an acid or a metal salt, and basically you have this displacement reaction take place. Well, a number of metals undergo these displacement reactions with acids to produce it produces salt plus hydrogen gas, okay? So when magnesium metal reacts with hydrochloric acid, it produces magnesium chloride, the salt, and hydrogen gas. So if we go ahead and try to assign our oxidation numbers using this bookkeeping system of electrons we just talked about, then we can see that magnesium originally has a 0, okay? And then in the reaction, or in the product, we see that now it has a +2 after the reaction. That means that the atom has lost electrons, and it must have been oxidized, okay? Because we remember that oxidation is loss of an electron. Now the oxidation number of the H+ from HCl, okay, actually decreases from +1 to 0. Thus it's gained electrons, meaning that reduction is gain, right? So it's been reduced. So the oxidation number of chlorine we see is -1 before the reaction takes place, -1 after, so nothing is either oxidized or reduced in that reaction, or for chlorine, it has not been oxidized or reduced. One key to remember is that when one substance is oxidized, another must be reduced, okay? And we can then look for the net ionic equation, which shows that the chloride has nothing to do with it, really. It's a spectator. So this leads us to the question of whether we can predict if a certain metal will be oxidized or reduced under various conditions. For example, if we took copper and we mixed that with silver, which will be oxidized and which will be reduced? Well, we can use the activity series to help us predict this outcome. Okay, and this is just a table which would be given to you. You do not need to memorize this. Okay, which helps us predict the outcome. The active metals, the most active metals, are the metals at the top of the table. These are usually the alkaline earth metals. Okay, they're most easily oxidized. So at the top, you're most easily oxidized, and these are going to form compounds easily. Metals at the bottom are going to be more your transition elements. They're very stable, they form compounds less readily. So any metal on this list can basically be oxidized by the ions of elements below it. Okay, so I like to think of the bottom as being the least reactive. Okay, it's this unresponsive, passed out, drunk, probably college student who really just doesn't want to do anything. Okay, and at the top you have Superman coming through, who's most reactive. He can replace anything below it in solution. So Superman. And the one key to know is that only metals which are above hydrogen in the activity series are actually able to react with acids to form the hydrogen gas. Okay, so these are a couple rules that are very important to know. So if we look at this reaction of copper and silver, and if we look at what's happening, we know that copper is above silver on the activity series. So I'm going to flip back just so you see that. So copper is just above silver in the activity series. Okay. And so if we take copper and we react that with a solution of silver, like silver nitrate, okay, the copper will replace silver and form copper nitrate. So basically what you end up seeing is that the silver is going to start to deposit on this copper tube, right? So you start to get the silver deposit, the copper is then being released into the solution, reacting with the nitrate to form a copper nitrate solution, which is blue in color. Okay, then you have that silver depositing on that copper wire. Okay, the reverse reaction will not occur. Right, if you put a silver wire in there and you react it with copper nitrate, the reaction is not going to occur. All right, now we're going to kind of turn our attention away from these chemical reactions, talk more of laboratory science. What would happen in the lab, and how do we make different calculations? And so now we can really talk about the aqueous solutions on more of a macro scale and the calculations that are associated with it. So a lot of times scientists use the term concentration to really describe the amount of solute in a solution. Okay? And we use the term molarity, which describes the concentration of the solution in moles of solute per liters of solution. Okay? It's abbreviated with M. Okay? I encourage you to make sure you memorize this formula. Okay, it's very important. It's probably just as important as when we talk about molar mass. So, for example, if you were asked to make 250 milliliters of a 1 molar solution, then you would first need to calculate the number of moles that are needed. Okay, and you'd find that you need 0.25 moles of copper sulfate. Okay, we would then dissolve that into 250 milliliters of the solution, which here is water. Okay. And you could also go back and convert, we don't have this balance that measures moles, right? So we need grams. So then determine how much we actually need to weigh out, we need to convert the moles to grams. But if we know it's a 1 molar solution, then we know we need 0.25 moles in 250 milliliters. And if you divide that, you get 1 mole. To express the concentration of electrolyte, this is kind of an important rule. You first need to examine the chemical formula of the compound. Right? For example, we can look at 1 molar of sodium sulfate, and we see that there's 2 sodium ions, basically because there's a 2 here, right, for every 1 sulfate anion. Right? So the concentration then of the sodium ions is twice as much, 2 molar, as the sulfate ion, which is 1 molar. Okay? If they're 1 to 1, then it's 1 to 1 in the concentration, like with sodium chloride. Another important note is that you can actually use molarity as a conversion factor. Okay, it allows you to convert from molarity to moles to volume to grams. So make sure you always keep that in mind, that if you have a 1 molar solution, that tells you that you have 1 mole per liter, and you could use that conversion in future calculations. So another thing we can talk about is dilutions. Okay, so many times in the lab, we have a solution that's in a concentrated stock solution. Okay, and we need to make a solution of lower concentration by adding water, and that's just making a dilution, right? If you have really strong Kool-Aid and you want to dilute it down, you make a dilution. If you have a really strong drink, right? Maybe you have some kind of like, Jack Daniels or something, and you want to dilute that down, well, you add a little water and dilute it down. Okay, so when making a dilution in the lab, the moles of the solute, or this is really in case of anything, but when you make a dilution, the moles of the solute will not change. Okay, the volume is going to change. And so change in that volume is then change in the molarity, right? Because we have moles per liter, liters are volume, and so if we change the amount, then we've now changed the molarity of that solution. And this is a good example to look at it as well. When you're calculating dilutions and you want to know what's the new molarity, and you're given the volume originally and volume after, and the original molarity, you can pretty much use this MV equals MV in most dilution problems. Okay, but this only applies to dilutions. So you can remember MV equals MV when you encounter certain dilution problems. Two more things. This is just more of going back to using molarity as a conversion factor, but you really need to understand that you can use that in a series of calculations. All right, so basically you could be given the molarity of a solution, and you need to calculate the number of moles, or you need to calculate the number of grams. You can have molarity. You can use the volume, get the amount of moles, convert those moles to moles of a reactant or a product to get the grams. So, you know, this is a good chart to kind of remember, figure to remember, and how to convert between those. All right, the final topic in Chapter 4 is titrations. I'm sure you're tired of hearing me talk, so I'll finish this up pretty quick. A titration is going to allow one to determine the concentration of a solute in a solution. This means that you combine a solution of known concentration with one that is unknown, right? Well, it's an experimental technique which really allows us to determine the concentration of that unknown solution. So basically all you do is you take a standard solution which is added to the unknown until they reach what's termed the equivalence point. Okay? And the equivalence point is just the point at which the solutions are going to be stoichiometrically equivalent. You can use these titrations titrations can be conducted using neutralization, precipitation, oxidation reduction reactions. A lot of times there's some type of indicator that tells you you've reached that equivalence point, or you monitor it using like a pH meter or so forth. And so in order to make a few different calculations using titrations, you can kind of remember this chart at the top. Okay. So lastly, I just want to finish up with this chapter is a lot of information. Okay, I really suggest you practice it a lot. Chapter 5 is slightly different. We're really going to start talking about thermodynamics and energy. So just really make sure you go through and practice a lot of stuff in Chapter 4. That concludes it, and hope you have a good day.